How to implement a stack data type in Golang. Hello, welcome back to my channel. Today we are going to implement a stack. Let's see what we will learn. First of all, we will discuss what is a stack actually. Then we will see how can we implement it in Golang in two different ways. Then we will make an application to see stacks in action. Okay, so first of all, what is a stack? So a stack is an abstract data type. It's basically an expected behavior. That's what abstract data type means. It's not a data structure. A data structure is a concrete implementation. Okay, so stacks are just some promises of a specific interface that should be respected. This is why it's called abstract data type. It does not enforce, this definition does not enforce a specific type of implementation. There are two ways to implement a stack. The expected behavior of a stack is a LIFO mechanism. That means last in, first out. So what does that mean? Basically, for example, if you have a pile of plates, you keep adding the plates on top of the pile, but then you can only take them from the top. Last in on the pile, first out. You take from the top. That's the promise of a stack. You can only operate on the top element. How can you implement a stack? So you can do it in two ways. You can use arrays, or slices in Golang, or you can use linked lists. And today we're going to implement both. So after we implement the stack in two different methods, we will be doing an application to see stacks in action. Some methods that we will implement: push, to put things on top of the stack; pop, to remove an item from the top of the stack; and peek is also a method that we will need to implement in order to look at the topmost item. This method will not alter the stack; it will just inspect the top element. Okay, so let's do these implementations, and we will begin by implementing a stack with arrays or slices in Golang. So let's say touch stack by slice.go. So here we describe our package main. Then we have the stack itself. So we would say type stack, which is a struct. And this stack will have slice of items. Items is a slice of type interface of anything. Okay, so we can put anything in there. So what we do right now is we need to write a constructor that we use in order to make sure that the items is initialized. So we will see exactly what that means. So func new stack, and this returns a pointer to a stack. We have a new stack, and then the point of using this function here is to make sure that we do this. We need to make sure that we initialize the items to an empty slice. Okay, so we will do make, we will do exactly this, interface and 0. So we will initialize items as an empty slice. So now that we have our stack properly initialized, we return its address. The only methods that we need to expose on the stack to be able to operate on it and to actually consider it a stack would be push, pop, and peek. So we have func. This works on a stack, and it's called push, and we receive an item which can be anything of type anything, and this doesn't return anything, but we will be implementing it soon. Then we have func, also available on a stack, which is called pop, and this will return an element of type anything. Okay, for now we just say return nil, and then we have the peek method, which is just a way to look at the top element in the stack. Func available on the stack peek. It returns us an element of type anything. Let's just say return nil for now. Okay, so these are the three methods that we need to guarantee that we provide in order to fulfill the requirement of a stack. Let's write some unit tests. Touch stack by slice underscore test.go. So now we describe the package, of course. And now we say, first of all, I would like to make sure that when I initialize my stack, when I create a stack, I want to really make sure that I initialize the items to an empty slice. Otherwise, if it's nil, because by default it will be nil, if it's not initialized and if it's nil, you cannot operate on it. So func, we want to make a test, ensure stack init with empty slice. In the scenario where we have a new stack, if s.items is nil, we want to throw an error. Right. So now let's see the unit test fail, first of all. So let's say so as you can see, I use the new stack constructor here, but let's say I don't have this. Let's say I do not have this initialization of items to empty slice. So if we would just return a stack with items like this, what would happen? Test. Right, so what happens is that our test fails, so we should always make sure that we initialize items. That's the purpose of this constructor. Otherwise, you can just return the address of a stack, and that's all. Let's rerun the test. Okay, so now the test is passing. Let's also write some unit tests for the push and pop and peek methods. So we have func test push, then we want to test pop, func test pop, and then we want to test peek, func test peek. So let's populate these unit tests with some expectations, and then we will go straight to the implementation. So in the scenario, in order to test push, in the scenario of a new stack, if we push 3 items, what should happen is if you have pushed A, B, C, then C would be on top. So if we look at the top element, we expect that C, so let's say actual top item is s.peek, and if actual top item is not C, then we throw an error. All right, so now we will fail, of course we will, because there is no implementation for push. Now let's write the implementations. If we think about it, we need to append the new item into the s-item. So we would just say s.items is append the new item to s.items. So this is all that we need to do. Now that we wrote the implementation, let's see the unit test. Go test. Why is the unit test failing when we wrote the implementation? Because peek has no implementation for now. It returns nil. Test push and peek. Just to be explicit about what we test here, let's also implement peek. What exactly does peek do? Peek just looks to the last element. What is the last element? That will be element at the last index. Okay, so last would be s.items at position length of s.items -1. This is the last element, and then we just need to return it. Let's see the test. As you can see, we're not modifying s.items. We are not assigning. We are just looking at what's on top of it. Okay, go test. So now the unit test is passing, which tests that push and peek work correctly. One thing we should test here is what happens if we peek into, this is an edge case, what happens if we peek in a stack that doesn't contain anything. So let's write a test for exactly this edge case. Func test peek, last it would be s.peek. And if last does not equal to nil, then we have an incorrect implementation and we need to throw an error. Okay, let's see the test. Go test. And we fail the test because index out of range -1, runtime error. And why does this happen? This happens because we are trying to access a length, we are trying to access the last element at a position of, since s.items length is 0, this would be -1. So first of all, we need to, if length.s.items is 0, there is nothing to peek at. So we just return nil. So let's see. Go test. So now we have fixed the unit test. So now we have verified that push works, that peek works. We have handled the edge case of peek looking at empty stack. Let's also add an expectation unit test for the pop functionality. In the scenario of a new stack, let's just push 4 items. If you fetch the last one, you kind of expect that the last one was D. Last is not D. We throw an error. You also expect that if you peek at what's remaining, the peek will return C. Let's see this unit test. And both expectations fail because there is no pop implementation. So let's go to the pop. It returns nil now. So let's think about the implementation for pop. First of all, we need to handle the scenario where pop from an empty list, or let's already handle this. If length of items is 0, there's nothing to pop, return nil. Last is s.items. Right, now that we have the reference to the last element, basically we need to reassign the slice to a version of it that does not contain the last one. So how do we do that? So basically we need to say s.items, new slice from 0 until length of s.items minus 1. And this construct we assign to s.items. Now we just return the last one. Let's see the unit test now. Okay, so now as we can see, the pop implementation works. Since we have added this check here in the pop, remember we added a check, is the S items first of all not containing anything, then we should just not return anything. Let's write the unit test for that. Remember, the purpose of the unit test is to make sure that later, if you write a different implementation, if you change your implementation of the pop method, if you broke something in the expectation, the unit test will fail. So then you have a certainty that as time passes and you change your program, the unit tests keep the consistency of implementations. Func test pop with empty stack. If we don't add anything into it, but just pop it, last would be s.pop. We would expect that the result is nil because there was nothing in it to pop. So if last is not nil, first of all, if it doesn't have that check in there, it's just gonna demand for a pop from out of bounds. So if we comment this, then we just don't even need this assertion here because the test will simply fail. Let's try to break it first. So as you can see, the test is failing on test pop with empty stack, and this is because we have commented out our check of returning nil if there is nothing in S items, and then we pop by demanding something from an index that does not exist. Right, now let's undo our comment to have the check back in place. Let's see what was popped actually. If the last is not nil, then we expect an error, and we also expect that the program doesn't crash, but that is implicit. We could just as well make this unit test like this with nothing here, and it would still be a valid unit test, because if the implementation fails, then the unit test still fails. This is how you assert in Golang that there was no exception thrown. You just don't add an assertion, and it will just fail. The go test command will fail if there is no proper handling. So let's add our check. So now let's rerun the test. And now we see that everything is good. Okay, this was the implementation of a stack behavior using a slice. Now we can also implement a stack by using a linked list. Let's see how to do that. So we say touch stack by linked list. Go, and we'll begin by describing our package here. Let's write our type. Now let's write our type. Let's call it ll stack from linked list stack. This is because we have already declared a stack type in package main, which is the other one. So let's just avoid confusion. So this would be the second implementation, ll stack. Okay, let's remember what the characteristics of a linked list are. First of all, the main characteristic of a linked list is that it has a head item. So this is something that should be present here as well. Head, which is of type item. Let's actually create the type of item, and then we say type item struct. This one has, as you can remember from the tutorial we made on linked lists, the items that you add in a linked lists must fulfill the expectation that each item points to the next one. So the items will contain two properties, which is data, which is interface of anything, and then the next of pointer to another item. Okay, now you can also maintain property size, which is int, and we will see how to implement. All right, so now let's write our so-called constructor, func new ll stack, and this returns a ll stack pointer, s, which is ll stack, and then s.size is 0 because it contains nothing when you initialize it, and then we return the address of s. Now, of course, we have the same, since we are guaranteeing that this is a stack, even if it's based on a linked list, we are guaranteeing the same 3 methods that should be made available on this stack, which are push, pop, and peek. And we will see the differences in just a second on how do these methods look when you use a linked list instead of a slice. Okay, so let's first add the dummy methods, the empty methods. So func as stack, no, a linked list stack. And then we need to push data, which is interface. We do not return anything. Then we have a pop method, func available on LL stack called pop. And this returns the last element. And then let's just say return nil for now. And then we have the peek method, and then it also returns us the last element, the element on top of the stack. Let's just say return nil so far. We can also add some method, let's say func length, which gives us the length of the stack. We just return the size of it. Now let's write our unit tests. So we have hatch underscore test. Go, and we describe our package, and here we just need the exact same unit test, the exact same expectations, but with a little bit of a twist because we have the different implementations now. Func test new stack must have nil head. So in the scenario of a new stack, s.head is not nil. I guess we can also make a test to ensure that the size property is set to 0. So func test new stack initializes size as if s.size is not 0. Let's run the test. So everything is good so far. Let's test the exact same expectations that we tested for stack by slice. Test push ll stack func test pop func test peek. Okay, so let's write the test for pushing. Actual is s.peek. If actual is not C, something was wrong. So this method, of course, tests push and peek. So if this was not so as expected, then error. All right, now let's see the test fail. Go test. Now we have a failure. So now we need to implement these 2 methods. So how do you think the push would happen in a stack that is based on a linked list? Well, remember that we have access to the head item. Since the stack always operates on the top element, you can essentially consider the head item as your top element. So basically, if you push an element, that will become your head. If you push an element into a linked list based stack that has no elements already, then your top element will be head. If you have elements, then you will push those further and your new element becomes again the head. So let's see how to do that. So what do we have here? We have, first of all, we have a new item. Item would be an item of data is data, and the next, remember that the item has data and next properties. Now we populate the data with the data that we sent here, but the next one, who do you think the next one will be? The next one will be what was already there in the head. So the next will be what was in the head. This can be nil, or this can be just something else. We just move what was there by 1 element because we added a new one. Okay, now this becomes the new head. No, this is the address of a new item. Okay, so this is how you will keep the functionality stack. And another thing we should do here is we should increase the size just to keep track of the new size. We have a push method here. It gets increased. Let's also solve the peek method. So first of all, what do we need to peek at? We need to peek at the last element on top of the stack, which, since we use a linked list, is always going to be the head. Basically, we want to see the property data on the item. Remember that head is also an item, so item would contain data and next. But if there is no head, we cannot see the data. In the case of head not existing, peek would give us nothing. If there is a head, we want to take a look at its data, so we just return s.head.data, and that's the peek method. So it's a bit simpler. There is no iteration needed because the top element is always the head. So now that we wrote our implementations, let's rerun the test. Go test. We can also write a unit test to make sure that this size was increased after you pushed. So func test stack size if you push an item, you expect that s.length is now 1, otherwise you return an error. Let's see this in action. Go test. Everything works. So we have tested push and peek. What if we peek an empty stack? Let's write the test for that. So twunk test peek on empty stack. This should not crash, so this test is already valid. We don't have to write an assertion, but basically we expect that the last is nil. If it's not so, we throw an error. Let's run a test. Go test. Let's also make sure that the pop works properly. So basically we want to test here. We want to test from a stack with elements, and we want to test from an empty stack. So let's write the test. So we push 4 elements. If we fetch the last one, if we pop, we have 2 expectations. We expect that the last that was popped is D, and we expect that the last remaining, the new last, would be C. Okay, so let's write these expectations. And if a new peeking is not returning C, let's run this test. Go test. Both expectations fail here because our pop has no implementation. Let's solve it. If there is no head, then there is nothing to pop. If there is a head, then we need to return it, and we need to change the linked list. Let's keep a reference to it. Let's say h is s.head. What gets sent in s.head is the next item. So s.head.next. What was previously as the next now becomes the head. Now we need to return h.data because that's the actual data. So let's see the test. Go test. Let's also test pop from empty linked list stack. Last is s.pop. First of all, the test should work until here. It should not crash. If it crashes, then it's already failing. If last is not nil, let's run this test as well. Go test. Right, so we have now completed our implementation stack based on a linked list. We have proven the implementation based on unit tests. We can also write a little application that actually makes use of these stacks. Let's do that. So let's say we imagine we have some, if you have used a graphics application, you can add filters on it, such as, blur, liquify, something from Photoshop. And then you can add a filter, then you can undo the filter. And then, so let's try to implement this idea. Touch, stack, app. Application.go package main. Let's say we have this graphics application, so type graphics app, which is just a struct type, and let's say we are trying to simulate the idea of an undo and redo system. So we will just use 2 stacks. So we have undo stack, which is a stack, and we have the redo stack, which is a stack. What's the idea here is that we have this application, and when we undo something, it gets sent to the redo stack. And when we redo something, it gets sent to the undo stack, and so on. Okay, so let's say we have some constructor that says new graphics app, returns a pointer to our graphics app, and then t.undo stack is a new stack. This uses the slice-based stack, and we will just test this application with both. And then t.redo stack is again another stack. And then we return the address of this. Let's say we have this function where we just apply some filter. So let's say on the graphics application, we have this function called apply filter. And then we just get a filter, will just be a string, doesn't matter. So then this just gets sent to, we make use of our push method. Remember, we have that on the stack. So we just add the filter on the undo stack. Okay. And then let's say we have these methods on the graphics application to undo and redo. So our graphics application has also a undo. And how do we move back and forth with one operation from the undo into the redo? We just get it and we say graphics application.undo stack.pop, right? Because we have undone something. I guess we can just call it undone. And then graphics.redo stack.push undone. Okay. And the other be also available on a graphics app. when we redo something, we need to remove it from the redo list. Redone is this. So then we put it back into the undo list. So then simply undo stack.push redone, right? So we essentially move back and forth between undo and redo. This is something you actually do commonly in such applications. So let's write a test to verify how this works. So let's say touch stack application underscore test.go. Okay, so we have the package main here. So we want to test two things. We want to test the undo and the redo method here. So we write some test for the undo, and then we write a test for the redo. We verify what we made here, these methods, with moving items back and forth from the undo to the redo. Oh, we need some comments here. So this is a constructor, this is the actual type. We save the file, it imports the testing. So, all right, so what do we test here? In the scenario of a graphics application, new graphics app, when we, use something in the application, so we apply some filter, blur, let's say. Since we have applied the filter, we expect it to be present in the undo stack, okay? If g.undoStack.peak does not contain blur, then we throw an error. Redo stack should contain nothing because nothing was undone. Let's run this, we'll test. So as we can see, it works. Test redo undo. Let's say we test both now. If we apply two filters, apply filter, let's say blur, and then we say apply filter liquify or whatever. Let's say we undo once, and then let's say we redo what we have undone, okay? In this scenario, if we peek in the undo stack, we have basically undone the last one, but then we reapplied it, okay? So that means this should be the peak, the result of a peeking in the undo stack. So if it is not so if undo stack.peak does not return liquify, we throw an error. Since we have redone it, we expect now that the redo stack is containing nothing. However, let's also undo both now. g.undo, just for fun. So what do we expect now? If we undo both, we expect both to be in the redo stack, okay? So then if we expect the undo stack to be empty, undo stack.peak, we want to see an empty undo stack. So if it's not so, and if ga.redo stack.peak does not equal, so what do we expect here? We expect that the last that was added in redo was, the first one that was added here. So if it's not blur, something went wrong. Okay, let's test this. Go test. And everything works. All right, so now what did we do? We have implemented a stack by slice. We have written the methods for this implementation. We have fulfilled the expectation of the stack abstract data type by using a slice. Then we have filled the expectation of it by using a linked list. We wrote unit tests for it. And then we have written an application that proves, by the way, we can also change our constructor here. Remember that we have two implementations. So as we can see, if we run a go test, our stack application works with the stack by slice. It uses new stack, which is a slice based. But if we change the constructor here to be new linked list stack, and let's change the implementation. We expect that the same application, the same behavior works with the switching back and forth between undo and redo. Okay, it should work because it's the exact same expectation of this abstract data type. It just uses a different implementation. So let's rerun the tests, this time by using the linked list based stack. Go test. As we can see, this also works. So now we have proven that both our implementations work with a concrete example, a simulation of a graphics application. All right, thank you very much. Please make sure to subscribe if you like this. It really encourages me to make new stuff. I will be continuing the series of data structures and algorithms. Thank you. Have a nice day.